Okay. Just so everybody realizes, there's a new homework. It's technically it's not available on paper yet, but it should be before class ends today. If not, it's available online anyway. It's due in 2 weeks anyhow. Homework 1 and 2 solutions are available online. Midterms on October 27th. There's no class next week. So there's a class on Monday. This is a Wednesday, 10/27. There's a class on Monday before that, but basically the week before the midterm, there's no class. I'm out of town again. So we have to cover everything in the next 3 lectures that I want to put on the mid. Okay. Any questions? Am I early? I got all these clocks. There's the CVN clock on the wall. Is it 10:10 yet? 9:10 yet? Yeah. Okay. I have my watch stops on me like at random points in time, so it's not all that reliable either. Okay. Last time we started talking about the Aloha protocol. Right, and let's go over what is the Aloha protocol. It's a very simple protocol. It's for collision avoidance. Okay, and the parameters we had were it takes time t to send a packet. Right, what else do we have in the system? There was a propagation delay of tau. And I think we said there are n+1 devices carrying the medium, n+1 transmitting devices, transmitting or sending, sharing the medium. Okay, so this is properties of the environment that the Aloha protocol is then built on top of. And the Aloha protocol just says let's see. When ready to send a packet, back off the time that's exponentially distributed right with rate lambda, and then send. And just hope no collision. Okay, that's how Aloha works. And if you remember the analysis of Aloha, what did we say? The propagation delay turned out not to matter all that much. What mattered was consider a device that sends at time t. Okay, so here's my timeline. At time t, I'm a device. I choose to send a packet. It takes me time t to actually send it. And then if you look at the, so this is the sender, or me. If you look at the receiving entity, if you look at timeline, then at time, let's say this amount of time is tau. Okay, then at time little t plus tau is when the receiver starts to receive the packet. Okay, up until time t plus tau plus capital T. Right, so this ends at time t plus capital T. Right? And the point was, if anybody else attempts to transmit to this receiver, when will that transmission result in a collision? Well, let's forget about the propagation delay for a second. Let's just assume it's 0. Okay? If some other device starts transmitting at time, any time between, so let me just draw this little bracket here and here. Okay, so this is time t minus t. If some other device starts transmitting right at this time, t minus t, then it will end right when my transmission starts, and they won't collide. Right? But if it starts transmitting just a little bit later, there will be a collision. Or if it starts transmitting a little bit after me as well, it will collide with my transmission. Right? Sort of imagine my hand being the other transmission. If it starts exactly at, and my hand's perfect size also. What a nice coincidence. Oh, all right. If it starts at time exactly t minus t, we'll miss. If it starts just a little bit later, there'll be some overlap, and that overlap lasts all the way up until the same point in time I'm transmitting. Now my hand's a little too short. And then also, even if I'm a little bit late. Sorry, if the other guy's a little bit late, even if he's after me, if he starts transmitting at any time until time t plus t, there will be a collision, right? And this propagation delay, for this case, where we're not sensing the line, where all we're doing is we're just deciding to transmit, it doesn't matter. We're both doing something at some time, and it's going to happen at the receiver delayed by tau. So if you have this delay of tau, you can just imagine what I said, these same overlapping points. The collision is going to happen at a time tau later than it would happen at the sender. Okay? People follow that logic? Okay. So basically the problem is there's an interval of time of length 2t over which no other transmitter can send if my transmission is going to get through. Okay, and that time is from t minus t. Sorry, let me just say the interval t minus t to t plus t. Okay. So anybody not get their homework number 1? I still have a few homework number 1 copies here. Okay. Okay. So well, I thought I might. Okay. I thought I might just sort of wave my hands over this, but I'm not going to. I'm going to be precise. So now we're going to make an approximation. Which, or you can look at it also as let's see, is it a lower bound or upper bound? They would actually be transmitting less. It means they have less likelihood of collision. Means a upper bound. Okay. Okay, we're going to look at the probability of a successful transmission in this setting. And to do so, we actually have to make an approximation. We actually have, the system is slightly different from what we're going to look at. So the small change, for the purposes of analysis, is that other devices can, each other device might send overlapping packets. With its own transmissions. Okay, something that would never happen in practice, right? I mean, a device, think of it this way. The way we're going to model this thing accurately is the device is going to set an exponential timer. That timer is going to trigger. It's going to send a packet. And while it's sending that packet, it's going to set another exponential trigger, okay, which may go off while it's already sending a packet. If that happens, it sends another packet, colliding with itself. You'd never do this in practice, right? It's stupid. You kill your own transmission. But for the sake of our analysis, we're going to do that because it lets us make the memoryless assumptions. Okay? So do people see what I'm saying? So for instance, the behavior of a device. Okay, at some time, let me not use t because I don't want to confuse people with the device that we are. At some time s, it starts to transmit. Okay, it's got this packet that it's got to transmit at time t, but it starts its exponential timer at this point in time, which may go off at this point in time, at which point the same device will send another packet colliding with itself. It's just for the sake of modeling. And of course, in practice, this overestimates the rate at which this device is going to send. Right? So you're more likely to get a collision here than you are in practice. Hence, it's an upper bound on the probability of collision or a lower bound on the probability of a successful transmission for our device. Okay? Well, so now the analysis is easy. So at time t, right, we're transmitting. The rule is just that no other device can transmit in this interval t minus t to t plus t. Okay? And all these other devices, they just set these exponential timers, which trigger at some point, and then they start to transmit when their timers trigger. Okay? If some device starts transmitting slightly before this time, that's okay. It's not going to collide with our transmission. And because it's a memoryless system now, because of this assumption, we don't care if devices are transmitting at this point in time or not. As soon as we get to time t minus t, now we care. And the question is just, does some other device's timer trigger during this interval of time? If any device, if its timer triggers, then there's going to be a collision with our transmission. If no device's timer triggers, then there's no collision with our transmission. Right? Okay? And by the memoryless property, the exponential distribution, we can assume the system slash experiment slash process starts at time t minus t. Right, everybody with me? By the memoryless property, we don't care what happens before this point in time, and at that point in time now we care. Right? So the probability is e to the minus 2 t lambda. That's the probability for a particular device that does not transmit within that time interval of 2t, right, when its timer is exponentially distributed with rate lambda. And then there are n devices to the nth power. So this is e to the minus 2t lambda n. That's the probability of successful transmission. Transmission is successful. Yeah, Ezra. Sorry. Are you saying that given that one device is transmitting? Yeah. Let's condition on the fact that our device is transmitted. Yeah. So right. It's easier just to say let's condition on the fact that our device is transmitting. If you want to know what's the probability, it's just hard to pick the particular point in time t is the issue. So let's say that at time t we know our device is, that's when we start to transmit. And given that, this is the probability of a successful transmission. Okay? So that's raw aloha. All right, any questions? Any other questions? Okay. Let's look at a version now where the device, let's make a small modification. Aloha with carrier sensing. Meaning a small change to the protocol. What that change is before transmitting, let's say it this way. When timer expires, device checks the medium. For an ongoing transmission. Okay? If no transmission, observed, send packet. Else, restart timer. Else restart timer. Okay? So the protocol is, okay, my timer expires just like in regular Aloha, but instead of immediately transmitting, I sense the wire. Okay? If I see some other devices currently transmitting, I won't transmit. You're right from there. You can see. Okay. Got it on me and not on the board. Okay. Right. So everybody gets what's going on here. We're just seeing the wire. Okay. So and remember the scenario that we'll call all devices are propagation delay tau from another. That's another simplifying assumption we're going to make to to facilitate the analysis. Right, so we all have this, if somebody's transmitting at time t, if somebody else starts a transmission at time t, I discover that transmission at time t plus tau. Okay? So it should be pretty easy to see that if tau is 0, there will be no collisions. Unless we start transmitting at exactly the same time, which happens with probability 0 in the continuous spectrum, right? But otherwise, if tau is 0, then you transmit, and right before I go to transmit, I check the line, and if you're still transmitting, then I see that and I don't transmit, right? So there's no way that I'm going to collide with your transmission, right? Everybody sees that? Okay, how do things work if let's have tau be less than t. Okay, so the time it takes us to send a packet is larger than propagation delay. I mean, this is pretty reasonable for normal environments. Okay, so how does this look now? Now we have to start really worrying about tau, because obviously you can imagine that if tau equaled t, right, then sensing the line would do absolutely nothing, right? Or if tau okay, before we consider this case, if tau is greater than or equal to t, okay, then sensing the line or sensing the medium is futile, right? It's almost like I don't know, the stars. You know, the light that we see from the stars today, the stars we see, that's actually light that's coming from millions of years ago, right? So, you know, if somebody told you that, I mean, nothing moves faster than the speed of light, but, you know, suppose that some bacteria could move very, very fast, right? And somehow they could, maybe I'm going on too much of a tangent here. You know, suppose, but you could look at these stars, and these bacteria eat stars or something, and you know they're going to eat planet Earth as well. And then, you know, you look at these stars, and you say, well, watch for the bacteria to eat them, and then we'll know if the bacteria are coming for us. But by the time the light reaches you, you know, it's too late. Dumb example. What's a better one? Oh, here's a good one that you'll appreciate as a student. So suppose your friend can get you the answers to an exam, right? Where tau is the amount of time it takes them to get the answers, right? The exam comes out and they can get it and get the answers and then get them to you, right? But if tau is bigger than t, where capital T is the time of the exam, right? If they get them to you before the end of after the end of the exam, it doesn't do you any good. So same sort of thing here, right? You're sensing the line, and if you see another device, if tau is greater than or equal to t, you're seeing some device that says, you know, it's transmitting, and you're like, okay, I won't transmit at this time, but it's already too late for your transmission to collide with what you're seeing, right? That's the basic idea. Okay, so the interesting case is tau is less than t, and is not 0. Okay, so what happens here? Let's see. So again, I'm going to start transmitting at time t, little t. Right? At time t plus tau. So let's do t plus tau. If no one started transmitting in this interval, then I'm safe, because no one's going to start transmitting after this point in time. Because if somebody starts, if somebody decides to start transmitting, let's say, slightly after t plus tau, they're going to see my transmission, right? It'll have reached them, so they're not going to transmit. Okay, so from t plus tau to t plus t, nobody else will start transmitting. right? Everybody see that? Okay, but I'm in the danger zone from time t to t plus tau, right? Carrier sensing doesn't buy me anything in addition to regular aloha, right? If I start transmitting at time t, nobody else sees that transmission until time t plus tau. Okay, so that's one kind of collision. So this is the risk zone, and then of course there's also the risk zone on the other side, right? Which is, let's see if I can get this right. If somebody else starts transmitting at a time tau before, right, I'm not going to see their transmission. But if they start transmitting at some time earlier, I will see their transmission. So they're at risk from time t minus tau up until here. Anybody who starts transmitting in this interval, okay, I'm not going to know about it, and I might sense the line and not see anything and start transmitting. Right. So there's also this interval t minus tau where it's going to cause a collision with my transmission. And then anything up until t minus capital T, right? Here I will sense it. Okay, and anything before that won't collide with me anyway. So now the danger zone, instead of being of length 2t, is now of length 2 tau, right? So the danger zone okay, and we haven't really changed any of the exponential assumptions, right? Because a device, when its timer expires, it's still an exponential distribution, and it looks to see whether or not there's a transmission on the line, and if not, just backs off again. So the process is still exponentially distributed. So the probability of a collision now is e to the minus 2 tau lambda n. Sorry, probability of no collision. I hope I said that before too. Yeah, probability of successful transmission. Probability of no collision. Yeah, that's right.
One line to another. So shouldn't it take 2 tau to see if the line, if someone transmitted?
No, because it's not like you're asking them, hey, are you transmitting? You're just listening, right? So the data always takes time.
You're not like sending a test.
Right. You just listen on the medium. Right. Okay, so that's aloha with carrier sensing. Yeah, Patrick.
Because it's all random, your device might not be able to try it indefinitely, right? If it keeps on hitting, sensing a line.
If every device is the same back-off time lambda, every device is equally favored as every other device. I mean, one thing to note about this protocol is there's no way to gain control of the line, hold on to it. The device who just finished transmitting has no benefit over the other devices. Actually, that's a good point. So the fairness of aloha. So think of carrier sensing without the backoff. Carrier sensing without the backoff isn't fair. Why isn't it fair? So suppose, the rule is if I have a packet to send, I check the line. If the line is clear, I send it. Okay, and if the line is not clear, I do a backoff. Okay, then once a device is successful at transmitting, right, let's say everybody's got lots and lots of packets to send. So if I could, I'd just keep sending and sending and sending. Then once a device grabs hold of the line, it's got it for good, right? Because I finished my transmission, okay? I checked the line's clear. I can start transmitting again right away, right? People see what I'm talking about? Or even if it was a fixed interval, you know, sometime like well, if it was a very, very small fixed interval, I'd finish my transmission, I'd wait this tiny little interval, check the line again. It's with very high probability clear, so I can start transmitting again. Whereas all the other devices, they would check the line with very high probability I'm transmitting still. And so they would have to do this short little back off, check the line again, and the likelihood they actually, you know, fall in the gap when I'm not transmitting is very, very small. Okay? Carrier sensing with the random back off. Let's see. I guess with the propagation delay, I do have a small advantage. Yeah, all right. The way I described it, the transmitting device is a small advantage. So I transmit during some period of time from t to t plus t, capital T. It kind of depends on how you look at the wave on the medium. So the problem with our model is that we said that while I transmit, it takes a propagation delay of tau to reach everybody else. But you can imagine that the line is clear for me as soon as I'm done with my transmission, right? I mean, I transmit from time t to t plus t, and now the line is clear. For me, immediately after that, whereas for everybody else, there's still noise until t plus tau. Right? Everyone else is still hearing my packet. So I have this small interval in which if my timer goes off, I get to keep the line, right? But imagine tau is much smaller than the expected length of this interval. Once this interval is passed, if my timer hasn't triggered, then by the memoryless property of the exponential distribution, all devices are equally likely to transmit again. Okay, and if the environment was such that I wasn't allowed to retransmit in this interval of time, then it would be completely fair. You know, so for instance, if I realized that the propagation delay was tau, and I said after I stop transmitting, I'll wait an additional tau before I try and transmit again. Then after this time tau, I restart my timer, and everybody else's timer has been running for some period of time, but because it's exponentially distributed, it doesn't matter. By the memoryless property, right, the game's all fair. The game's completely even once all timers are running. It doesn't matter for how long they've been running. Okay. Yeah.
Going back, without carrier sensing, how do you know whether to send it again? If you're not sensing the alarm.
Oh. So suppose you do sense the line, but not for the purpose of delaying your transmission. So imagine every device has a sending component and a receiving component, and receiving component might be able to tell the sending component, hey, don't send yet, right? The line's busy, but maybe it doesn't. Maybe the sending component just sends whenever it feels like it, and so you still listen to the line. You still tell. You're still listening to all. Every device is a sender and a receiver. You're still listening to hear whether other devices are transmitting. And you can learn later on whether or not your transmission made it through. Or maybe the other device sends you a message that says, please resend your packet. It's a good question, but it's sort of outside the scope of the analysis. So there's some way to determine whether or not packets are bad, and maybe it's by sensing line, or maybe it's by some other means. Maybe it's retransmissions or something. Maybe the devices just keep trying to retransmit. We never said that every time it transmits a packet here, it's new information, right? It might be repeating old information. Okay? Okay, and then there's one other version of Aloha I want to cover, which surprisingly improves the performance, although you might not initially think it would. And that's slotted Aloha. Okay, in slotted Aloha, devices have synchronized clocks. Okay, so note that Aloha and carrier sensing Aloha never really needed device clocks to be in sync with one another. There was no timing mechanism. And time is divided into chunks, or into slots. Of size capital T. Okay, right, so here's time. And there's our slots. And you're only allowed to send a packet in an interval of time T. So with Aloha, right, you could send a packet at any arbitrary time. It could pass over both intervals. So the way slotted Aloha works is if your timer expires in this interval, during slot, let's say I-1, then you send the packet in slot. Okay, so again, you set the exponential timer just like you did in Aloha. All right, your exponential timer goes off at some point, and you don't send your packet immediately. You wait till the next slot. So if my timer goes off at any point in this interval, I'll then send my packet in the next interval. Okay, restarting my timer right away, such that if I have another packet to send, if the timer goes off again in this interval while I'm sending, that just means I send in in the next interval as well. Okay, so people understand the protocol? Set your timer. When it goes, again, it's exponentially distributed. When it goes off, that means you're sending in the next interval. Okay? Stay advanced. All right? Everybody clear on that? So what's the probability of collision? In slotted Aloha. Without carrier sensing. Okay? Well, suppose my timer goes up at time t. Okay, so I'm going to send the next interval whenever that starts. So suppose the next interval starts at some time t plus s. Okay, so this is t is when my timer goes off. T plus s is when is the start of the next interval. Start of the next slot. Okay, so my transmission goes off during this slot from time t plus s to time t plus s plus capital T. Right? So when can other devices not transmit? In order for my transmission to be safe, to make it through. Okay, t plus s minus t to t plus s plus t. Right? Again, an interval of size 2t, 2 capital T. Right? Let's say they're also running the slotted aloha protocol. Right? Then they're not going to start at some arbitrary time. They're either going to start at time t plus s, right, because that's one slot, or at time t plus s minus t, or at time t plus s plus t, right? That's where the slots are. So I only have to worry about the other devices whose timer causes them to send a packet in this interval. If they send it in this interval, there's no collision. If they send it in this interval, there's no collision, right? And when would they send in this interval? Yeah, David.
Are we assuming the interval is longer than the time it takes to send the message?
The interval matches the time it takes to send the message. The message is of length capital T, and the intervals are of size capital T. Yeah, Ron.
What you have to worry about is the probability that the timer goes off in the previous.
Exactly. You just have to worry about the probability that the timer goes off in the previous interval. If another device's timer goes off in the previous interval, then it's going to collide with your transmission. Right? Doesn't matter if the timer goes off during your interval. Doesn't matter if the timer goes off prior to that interval. All we care about is if no other device's timer can go off during the previous interval. Right? And what's the probability that an exponentially distributed timer goes off in this interval? Or what's the probability an exponentially distributed timer does not go off in this interval? Right? The prior history doesn't matter because it's memoryless. And this is the probability that a timer doesn't go off during time period t. Right? So this is e to the minus lambda t. And then there are n devices, so times n. Okay? So, for aloha, you've got e to the minus 2t lambda n. It's really an upper bound, but it's sorry, lower bound on success. Yeah, you're more likely to be successful. Lower bound, but very close for large n and reasonable lambda. Let's not worry about that. Okay. For slotted aloha, it's e to the minus t lambda n, and for aloha with carrier sense, it's e to the minus 2 tau lambda n. And this is when tau is less than t. Gesundheit. Right? Is it worth covering aloha with, slotted aloha with carrier sensing? Why not? Yeah. There's no point in adding carrier sensing to slotted aloha because we've already got it where basically with the slots we're coordinating the transmission times of all devices. They're all going to start transmitting at exactly the same time. So given any propagation delay whatsoever, your carrier sensing isn't going to help you to detect that, right? Carrier sensing will only help you detect somebody transmitting in the previous slot, which isn't going to collide with transmission anyhow. So carrier sensing won't give you any additional benefit, right? Yeah, Ron.
Can you explain why we get a specific expression for the probability that no other device's time is going to go off in the previous interval?
Yeah, the previous interval has length of time t, right? There are n other devices, okay? And you've got this interval, okay? So imagine time is going by. You enter into the interval. We've just entered it, okay? And the various times have been backing off for different amounts of time, based on whatever, the last time the timer triggered. Doesn't matter. It's exponentially distributed, so it's memoryless, right? So it's as if the timers all started right at this time, t plus t, whatever, t plus s minus t, where the interval started, right? It's like they all started here, and now all we got to make sure is that none of those other timers go off before time t plus s, right? This length of time t.
So that would be then for like 1 minus probability that it does happen in each of those cases?
Yeah, but the probability that so okay. So what's the probability that that time is greater than t? Where this is so let's call it x. X is the let me try and it's a very good question. So here's the timeline. Okay, here's end of a slot. Okay, here's the end of the next slot. Right. That distance is capital T. Okay, and let x, the time that device 1's timer goes off. So this happened to be the time that I was calling t plus s minus capital T. Right, just to match up with what's above there. The time that device 1's timer goes off, let's call it device 5. I mean, it doesn't matter which device, just a device other than me. Device 5 timer goes off the next time after, let's say the first time that device 5's timer goes off after time t plus s minus t. Okay, so its timer has gone off many times before this point in time, but we get to this point in time and I'm asking, when's the next time it's going to go off? Right? And I would just want to know what's the probability that x, which is a random variable, is greater than t. I mean, they're both capital letters, but t we've been using as a constant. Right? If this time is greater than t, then device 5's timer does not go off in this slot. Right? And it's an exponentially distributed random variable with rate lambda. So it's memoryless. I don't care when the last time the timer went off. Right? I'm just looking from this point in time to the next point in time when it goes off. The probability that time is greater than t is just e to the minus lambda t.
So the reason I asked is because if you're talking about all the other devices, then would it be n minus 1 n is the number of devices?
There are n plus 1 devices. Counting you.
N plus 1 I thought it was n total.
Oh, I erased it. No, it should have been n plus 1. I made it n plus 1 just so, otherwise everywhere we had n, you have to have minus 1. Right, so this is just for one device. And then for the n other devices, c to the minus lambda t to the n power. right, which is e to the minus and the tn. Yeah.
But if the probability that the timer goes off is that, he asked me before, and I guess I didn't hear that.
No, there's a probability it does not go off. The probability the timer does not go off. The probability that x is bigger than 2.
Right, okay.
So I just want to make an interesting comment. Tau is less than t, so aloha is definitely the worst. E to the minus 2t lambda n will be smallest. And then which of these is better, slotted aloha or aloha with carrier sensing, depends on the size of tau, right? So if tau is less than t over 2, better to use carrier sense than slots. If tau is greater than t over 2, better to use slots. Right? Okay? Any questions? Okay, we're gonna switch gears a little bit, get off the stochastic stuff, and actually get back into the coding stuff for a bit, but for collision avoidance as opposed to for error detection and correction. And we're going to look at CDMA, or a very simple version of CDMA. So code division multiple access. Okay, which, your cell phone, most of them have CDMA technology and blah blah blah. There's a lot more to it. The advantages that the cell phone uses, it's harder to jam, it's harder to decipher, but we're not going to worry about any of that. It's going to look at how CDMA can be used to help devices transmit simultaneously on the same line. So, okay. Again, devices send Boolean signals. But instead of zeros and ones, they send ones and minus ones. Okay, so positive, negative voltage, whatever. But they send the values are plus and minus, and the signals of multiple devices are additive. Okay, so 3 devices. One sends 1. One sends 1. I should say another. A third sends minus 1. You just add the 3 together, and you get a value of 1. If they all sent a value of 1, all right. So if they all sent 1. You get a value of 3, and if they all sent minus 1, you get a value of negative 3, etc. Okay, so the signals are just additive. Okay? Okay? Each device has a series of what are called chirping bits. Okay? So for instance, device 1 may have the chirping sequence, chirping bits slash chirping sequence. Might have the chirping sequence 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. Okay? And to send a bit of 1, it sends its chirping sequence. And to send a bit of minus 1, it sends its negated chirping sequence. Okay, so in order to send a bit of data, you have to send out this chirping sequence each time. So there's, in some sense, there's a high overhead because in order to send any bit of data, you have to send out this chirping sequence. So if I want to send out a 1, I have to send out this sequence 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. If I want to send a minus 1, right, the opposite value, the equivalent of 0, I'll send minus 1, minus 1, 1, 1, minus 1, 1, minus 1, 1. Negate every bit. Okay? So let me just say that as an example. E.g., to send data bit sequence 1 minus 1 minus 1 with chirping sequence 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. So you'd have to send 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. That's to send the 1. Right? And now I have to send the negated sequence. Minus 1, minus 1, 1, 1, minus 1, 1, minus 1, 1. That sends a minus 1. And then do that again for minus 1. Minus 1, minus 1, 1, 1, minus 1, 1, minus 1, 1. So everybody understands how to send out the chirping sequence? Okay. The rule that we'll need is that any two devices that share the transmitting medium must have orthogonal chirping sequences. Okay, orthogonal means if the chirping sequence for device 1 is 1, 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, and C2 is something else, then C1 dot product with C2 has to equal 0. Okay? The dot product, you just take it term by term, you multiply together, and then you add them up. And if that comes out to 0, they're orthogonal. Okay, so for instance, R 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, and 1, 1, 1, 1, orthogonal to one another. So that's C1, C2, C3. Okay? Well, C1 dot C2 is what? It's 1 times 1 plus 1 times minus 1 plus 1 times minus 1 plus minus 1 times minus 1. Right? Which is 0. So C1 and C2 are orthogonal. Okay? And you should be able to eyeball pretty quickly that when you take C1 dot C3, you're going to get 0, and C2 dot C3 is also going to give you 0. Right? Because it's going to be 1 plus 1 minus 1 minus 1, and 1 minus 1 plus 1 minus 1. Okay? So they're all orthogonal. Okay? So suppose with that C1, C2, C3, this is 1, 2, and 3. With chirping sequences. So 1 equals, let's just go with that again. 1, 1, minus 1, minus 1. So 2 equals 1, minus 1, 1, minus 1. And C3 equals 1, 1, 1, 1. Send bits 1, minus 1, minus 1 respectively. Okay, so device 1 wants to send a bit 1, device 2 wants to send a bit minus 1, and device 3 wants to send a bit minus 1. Okay? Then what's transmitted on the medium is, right, C1 is going to send 1, 1, minus 1, minus 1. C2 is going to send the negated value of its chirping sequence, minus 1, 1, minus 1, 1. And C3 is also going to send the negated chirping sequence, minus 1, minus 1, minus 1, minus 1. So what you get on the medium is going to be minus 1, 1, minus 3, minus 1. Okay, so this is what goes across the medium. This is the chirping sequence that traverses the medium. Okay? Everybody follows? Just take the chirping sequence. If you want to send a 1 bit, you send your chirping sequence. You want to send a minus 1 bit, you negate your chirping sequence. You send it out over this medium, and it's an additive medium. Okay? So if device 1 wanted to send a 1, device 2 wanted to send a minus 1, device 3 wanted to send a minus 1, and these were their chirping sequences, this would be the chirping sequence that actually traverses the medium. Okay? suppose I'm a device now and I want to get, I want to receive these signals, but I'm interested in device 1 signal. I'm not interested in device 2 or devices 3 signal. How do I obtain so what was it? It was -1, 1, -3, -1. Right? And the way you do it is well, the device 1 transmitted bit so let's call this will be R, the received sequence is going to be R dot product with device 1's chirping sequence, okay, divided by the size of R, or the size of C1. They're both the same. They're both 4 bits long. So this is the length of the chirping sequence. Right. So for instance, device 1's bit I'm claiming is -1, 1, -3, -1, dotted with 1, 1, -1, -1, divided by 4, which is -1 plus 1, so I'm at 0, -3, sorry, plus 3 plus 4. Sorry, -1 plus 1 plus 3 plus 1 comes out 4. And then you divide by 4. So you get 1, which is indeed what device 1 tried to send. Right? And device 2's bit, device 2's bit is going to be this -1, 1, -3, -1, dotted with 1, -1, 1, -1. Yeah. Which is going to be -1, -1, -3, plus 1. So -4. And that divided by 4. -1, which is indeed what it tried to send. Right? And device 3's bit is this -1, 1, -3, -1, dotted with its sequence 1, 1, 1, 1, which is going to be -1 plus 1, -3, -1, which is again -4, divided by 4. Right? So it worked out. Pretty neat. Okay. Why does that work? That's question to be answered. Well, what did we do? Why did that work? Okay, let B1, B2, B3 be the bits these 3 devices wanted to send. Right, so then what was sent over the medium was B1, C1 plus B2, C2 plus B3, C3. Right? Just multiplying the sequence by the bit. Okay? Retrieve device 1's bit, or device I's bit. We did, all right, this was this quantity R that we called. We did R times R dot producted with C sub I, right? R dot product C sub, oh, and then we divided by the magnitude of R. R dot product C sub I divided by R is what if we write it out? It's B1 C1 plus B2 C2 plus B3 C3. Right, this whole thing dotted with R. I mean, sorry, dotted with CI. Right, divided by the magnitude of R. Which, if I just apply the associative rule, the commutative rule, I don't know, is B1 C1 dot CI plus B2 C2 dot CI plus B3 C3 dot CI. Right? Divided by R. Okay? And by orthogonality, C1 dot CI equals 0 unless, let's just say Cj dot Ci equals 0 unless I equals j, right? And then it equals then it's just the magnitude of the number of components of Cj or Ci, right? You dot product something with itself where each component's 1. It's going to work out to be the number of terms. So basically all we're doing when we take the dot product with the Ci is we drop out all the other components except the one that we're looking for. Okay? So for instance, if I equals 1, then R dot C1 over R is just going to be B1 C1 dot C1 plus B2 C1 dot B2 C2 dot C1 plus B3 C3 dot C1 over the magnitude of R. Okay. These are 0, right? And this becomes, so it equals B1 times C1 dot C1 over R, and I'm just saying that this equals R. So you get back the bit B1. I'm going to put it there. That's equal to R. Okay, so it's a cute little method. Let me just quickly go over a cute way to generate orthogonal codes. It's called the Hadamard matrix. How to use Hadamard matrices. Okay, so the ith Hadamard matrix is the ith Hadamard matrix, let's call it H sub I, is going to be the matrix formed by H sub I minus H sub I minus H sub I minus H sub I. Sorry. Minus 1, minus 1, minus 1. Okay, so you make the ith Hadamard matrix by taking 4 I minus 1, I minus first Hadamard matrices and sticking them in and negating 3 of them. So let me show you by an example what I'm talking about. So H sub 0 is going to be the matrix with a single entry 1. Okay, and then H1, I'm going to take my H0s and put them in. So what I'm saying is it's H0 minus H0 minus H0 minus H0, which is going to be 1 minus 1 minus 1 minus 1. Okay, and Hadamard matrix 2 is going to be, first I put my Hadamard matrix 1 here, okay, and then I put negations of my Hadamard matrix 1 in the other components. So it's minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1. Okay, so there's your H1, and then here are your 3 negated H1s. Okay, and I can continue the process. H3 is going to be a very big matrix. 1 minus 1 minus 1 1 minus 1 minus 1 minus 1 1 1 1 minus 1 1 1 1 minus 1 1 1 1. Right, so there's my H2, and then I have to negate it and put the negated version over here. Minus 1 1 1 minus 1 1 1 minus 1 minus 1 1 minus 1. And then do the same thing down below. The same thing over here. Okay, so there's my H3, and you keep doing it, okay? And turns out that each row is a chirping sequence. Orthogonal to every other row. Right, so H sub I contains 2 to the I orthogonal chirping sequences. The homework went around? Everyone got a copy of the homework number 3? Okay. Okay, any questions?
Is it HI minus 1? All of them.
All of them. But the one on the top left is the HI minus 1, the other 3 are the 8. Any other questions? Okay.
Yeah. So if there's an error on the line, then all of the are affected every.
Yeah, and we're not going to look at how to combine CDMA codes with error recovery, but you can imagine you could sort of use the Hamming distance idea. You go to the closest. Instead of getting 1 or minus 1, you'll get 0.95. So it'll be 1 instead, depending on the extent of the error of the noise on the line. So.
To the what?
2 to the I orthogonal matrices.
Right, there's 2 to the I rows. So double each time.